So, the key to understanding rocks is understanding that the building block to life is this carbon molecule because it's got these four bonds, and so you can make three-dimensional structures out of this, and so you've got the infinite complexity of life. Now, with silicon, it's just below it, and it does the same thing. It can form these four bonds. But these four bonds are actually with oxygen. So the silicon's the black, usually black's carbon, and it's got these four oxygen tetrahedrals, just like diamond. So you need to remember that this is the strongest known natural substance, and that's for life. That's diamond, even though that's not alive. And the similar structure is silicon dioxide because they start sharing these oxygens. So the ratio is actually less, even though it's the tetrahedron itself is silicon tetraoxide. Okay, so the key is these rocks, these infinite number of rocks, all center around that tetrahedral shape from silicon, and the building block of life is the tetrahedral shape of carbon. Now, while we're still on the periodic table, most of the elements are below this. So these are all like the gases, and they're all released and in the atmosphere. And the silicon binds with four oxygens, so it's relatively light, which is extremely important. So it floats and it's less dense, and it's in the cooler parts, so it can solidify. So you've got to remember where basically Earth is just a molten blob of rock, and there's this little tiny part on the edge that has cooled down and become hard, and that's what we live on. But the majority of the Earth is just liquid rock. So we're just looking at the very edge of the rock when it's cooling, and these things are more heavy. The majority of the elements in the metals that are all positive. So these all form positive charges, and they normally just stay inside here. So it's only the stuff that's light enough to float to the top that's going to become rock, and that's what we're going to see. And that's what we see with silicon dioxide. It's on the top half here, whereas the majority of other elements, because silicon's linked to four oxygens, this is only much less weight than all of these other elements further down the periodic table. So it is lighter and it goes to the top. So just before we get into all the minerals, just to highlight, so that has a 4+ charge, and this will have a negative charge, sometimes written as 2 negative. And those charges will attract all of the positive metal ions. And so that's going to determine what sort of minerals we get. Also, they join up and they can share. Okay. So it's just important to know that there's a positive charge in the middle, and that's attracting the four oxygens, and so there's a negative charge on the outside. Just so I can, just for further links, for further studies, sometimes you can have aluminium in there, it's not as stable, and the aluminium can form this octahedral, so it's got 2, 4, 6 things that can fit on it. So now we get into things proper now. So what you can see here is what you have really high temperatures, and then eventually it just gets cooler and cooler and cooler until you get to the crust. Until you get to the actual magma cooling, we don't have any rocks yet. And so it has to cool for the rocks to form. And initially what you're going to have is you've got too much energy at these high temperatures. So the silicon dioxide structures can only be singly, and then when it gets more stable, they can go to chains, and then maybe double chains, and then maybe even sheets. And then finally, the strongest one we have, which is resistant to weathering, is the three-dimensional structure of these all linked up together. And so what you're going to have is a stability formed as the cooling process occurs. You can also see that if you have a careful look at the ratio of SiO4 to, there's two metals here, and you have a careful look at the structure, you'll see that the ratio of silicon dioxide to metal is also decreasing. So there's more silicon dioxide as there are more of these tetrahedrals joining up. So the ratio of metal is less to silicon dioxide. And so as you would expect, because of that ratio, you would expect that the density is also changing. So you can see that the densities of the earlier minerals up here are much higher than the densities of the more common minerals here. So you can see that what you're going to end up seeing is you're just going to see the lighter minerals and you're not going to see these heavier minerals. And that's because these heavier minerals, you do see they're much rarer. What they actually do is they form, but because they're more dense, they sink back into the magma chamber and melt. And so you don't get them as common, and these ones here won't sink and they'll float, and so they'll actually be able to solidify and form and stay on top of the magma where the crust is. And so that's why pretty much all the rocks you see pretty much are quartz because it doesn't weather, or they're these things or these things that have further weathered, and we're just going to go into the further weathering a little bit more now. And just if you're interested in further reading, there are further structures giving further elements, and there's just a little bit more detail. All the references are in the end. And so trying to cover all the minerals based on silicon dioxide, this is at just normal temperatures and pressures, so just on the surface. And so the majority of minerals you're going to see already, I've told you, are just quartz and feldspars, and quartz don't weather. And so the only other thing you're left with now are feldspars, and the feldspars change into kaolin. And then, of course, you do see all the other minerals in small amounts, and they turn into various other things. And so what's going to happen now is you're going to see that the silicon dioxide tetrahedrals form, as they weather, they manage to form into more and more complexity sheets. And you might be thinking, well, how come we just don't go all the way to quartz? Well, these sheets have materials in them, so there's negative charges here, and you've got various metals in them, and it wouldn't be possible to extract them unless you melted the whole thing again and let it form slowly, so that quartz crystals could recrystallize. Otherwise, they're trapped in between the sheets. So when you grab these clays and fire them to turn them into ceramics and pottery, it forms that chemical structure with these stuck in there because they're trapped in between the sheets and they can't come out. So you can't just heat everything up and get it back to quartz. It also explains the other method. So these are clays. So all of the minerals we've talked about up here, as they undergo chemical processes and pressure and temperature, they then start to form these further sheets, and so they form further complexity of the tetrahedral shapes. Now, the other thing that forms is, besides these clays through the weathering, they also form the metamorphic rocks, and so they reform into these quartz with enough heat and pressure, and also the mica layers. So when you look at the schists, you'll see like the granite will reform these more complex sheets and three-dimensional tetrahedral layers. So it sort of explains all the metamorphic rocks as well. All right, so I've explained all of the igneous minerals, and then now I'm explaining here all of the clay minerals. And so we're pretty much done. The only thing I've left out are just, for me as a chemistry teacher at least, just the simple chemical reactions. So the calcium carbonate, it's just the simple ionic compounds, and so the calcite and the hematite, which is just, is just oxidized iron. So that's Fe2O3 or FeO. So the simple chemical reactions I've left out, and they are some semi-common minerals. I've just dealt with the more complex ones, which are the igneous minerals, and then forming the metamorphic, going under the alterations through metamorphic, and then going under alterations to all the clay minerals. And that pretty much covers every mineral there is. And it's all based on that tetrahedral structure, how easily it can form. So here are the references. So I think I've given you an understanding how the silicon is the building block of all the minerals. Now that you know the minerals, you'll understand all the rocks, and hopefully you know the rocks, you'll understand the macroscopic geological formations, and then you'll understand, be able to interpret all the when, what, why, how from that. Okay, so hopefully that makes sense of rocks.